Hello, and welcome to this second presentation related to the application of Macaulay's method for finding slopes and deflections along simply supported beams. This lecture is underpinned by a previous presentation where we introduced Macaulay's method, outlined the theoretical background, the limitations of the theory, stated sign conventions, and showed the basic procedure used in generating the bending moment equation and then integrating this to find the slope and then the deflection equations. Within this lecture, we're going to consider several exercises that will be outlined initially, and I would encourage you to attempt, but the full work solutions will be included. Exercise 2. We're asked to calculate the central deflection for the simply supported beam shown in the sketch. So here's our simply supported beam. If the second area moment, the I value is 40 times 10 to the negative 6 meters to the 4, and the Young's modulus E value is 200 giganewtons per meter squared. We're also asked to calculate the gradients or the slopes at the ends A and B of the beam. So we need to find what the slope is here and here. We have 2-point loads applied to the beam. We have 30 kilonewtons, it's 2 meters in for the left-hand end, and 60 kilonewtons, that's 4 meters in for the left-hand end. The overall length of the beam is 6 meters. Answer is given here in the brackets. This is the reaction RA. Left-hand end reaction we'll need to calculate. The deflection, the centre of the beam is 43 millimeters. And then the gradients or the slopes, left-hand end positive 1.24 degrees and right-hand end negative 1.3 degrees. So what we're going to do now is use Macaulay's method to generate the appropriate equations and solve for the central deflection and the gradients at the ends of the beam. So exercise 2M, here's the solution. The first thing we need to do is calculate the beam reactions. And this goes back to our previous presentations where we had to calculate beam reactions by taking moments about a point. We're taking moments about RA in this particular case. For equilibrium, the summation of all the moments about point A must equal to 0, and we've got clockwise moments are positive in this case. So taking moments about point A, clockwise moments we've got 30 kilonewtons multiplied by 2 meters, so that's 30 times 2. Also clockwise we've got 60 kilonewtons multiplied by 4 meters, it's 4 meters across here. And anti-clockwise we have reaction RB multiplied by 6 meters. So in our equation that will be minus RB times 6. Rearranging for RB is equal to 50 kilonewtons. To calculate reaction RA, we summate vertical forces. So summation of all the vertical forces must equal to 0 for equilibrium. And in this case, upwards forces are deemed positive. So summating the vertical forces, upwards RA, so that's positive RA, the 30 and the 60 kilonewtons are downwards, so that's minus 30 minus 60, and then reaction RB, we calculated above, is 50 kilonewtons, that's positive 50. Evaluating reaction RA is 40 kilonewtons. Next we need to calculate the bending moment along the length of the beam, and to do that we're going to use the second order differential equation. And that equation is stated as negative EI multiplied by the d2y by dx squared is equal to m. It's this EI term we need to calculate, and the EI term is sometimes referred to as flexural stiffness. So we know the E from the question is given above. The E is 200 giganewtons per meter squared, so that's 200 times 10 to the 9 newtons per meter squared. And we multiply that by the I, which is 40 times 10 to the negative 6. So multiplying those two terms together, we find the flexural stiffness is 8 times 10 to the 6 Newton meters squared. Notice the units of flexural stiffness is Newton meters squared. Exercise 2M continued. So what we're going to do now is generate an equation for the bending moment along the length of the beam. We're going to integrate to find the slope. We're going to integrate to find the deflection. Then we're going to impose our boundary conditions. So as always, we start from the second order differential equation of bending. So the negative EI multiplied by d2y by dx squared is equal to m. We've calculated the EI from the previous page. It was 8 times 10 to the 6 Newton meters squared. And I'm using the shorthand notation here. The y double dash is d2y by dx squared. So noting that x is running from left to right and the reaction is 40 kilonewtons from the previous slide, we can generate our bending moment equation. So it will be, in terms of a function of x, 40 times 10 to the 3 times the x value minus 30 times 10 to the 3 times x minus 2. So there's my 30 times 10 to the 3, x minus 2. And then minus 60 times 10 to the 3, x minus 4. So there's the 60 times 10 to the 3 and the 4 because we've got the 2 add to 2. So equation 1 is the bending moment equation. What we're going to now is integrate to find the slope equation. So integrating the left-hand side of equation 1, we get negative 8 times 10 to the 6 y dash. Don't forget y dash is dy by dx. On the right hand side, integrating the standard forms again, we will get 40 times 10 to the 3 x to the 2 upon 2, and that simplifies to 20 times 10 to the 3 x squared. Integrating the second term, we'll get negative 30 times 10 to the 3 times x minus 2 to the power of 2 upon 2, and that simplifies to negative 15 times 10 to the 3 x minus 2 squared. And integrating the third term of equation 1, we'll get negative 60 times 10 to the 3 x minus 4 raised to the power 2 over 2. And the third term simplifies to negative 30 times 10 to the 3 x minus 4 to the power 2. And then I add my constant of integration, C1 here. Call that equation 2. Integrated one more time, we will find the deflection equation. Notice that y is the deflection. So we end up with negative 8 times 10 to the 6 multiplied by y, and that's equal to, integrating the first term of equation 2, 20 times 10 to the 3 x to the 3 upon 3. Simplifying the first term, 20 times 10 to the 3 divided by 3 is 6.6 recurring times 10 to the 3 x to the 3. Integrating the second term, that becomes negative 15 times 10 to the 3 x minus 2 to the power of 3 upon 3. That simplifies to negative 5 times 10 to the 3 x minus 2 to the power of 3. And integrating the third term of equation 2, that becomes negative 30 times 10 to the 3 x minus 4 to the power of 3 divided by 3. And that simplifies to negative 10 times 10 to the 3 multiplied by x minus 4 to the power of 3. We're also integrating the constant C1, so that becomes C1x. And of course we now have to add constant C2 as we've integrated a second time. That gives us equation 3. Let's consider the boundary conditions now. Where do we know a deflection or a slope along the beam? Well, we know when x is equal to 0, that's at end A here, there will be no deflection because we're on a support, so I've called that equation 4. And when x is equal to 6 meters, that's the other end of the beam, our B, again there'll be no deflection. We do not know in this case the slope at any point on the beam because the load is unsymmetrical here. Exercise 2M continued. Just repeated equation 3 for convenience here, along with our boundary conditions labelled 4 and 5 here. So we're now going to substitute equation 4 into equation 3, and we can clearly see that C2 is equal to 0. Just think that through for ourselves. So if y is equal to 0, that term will disappear. If x is equal to 0, that term will disappear. The second term will disappear here because x minus 2 would be 0 minus 2. That would be a negative inside the bracket, and we ignore negative brackets with step functions. And the same applies to the third term here. C1 times x will also be 0, so therefore C2 must equal to 0. If we now substitute equation 5 into equation 3, this time we've got x is equal to 6 meters and y is equal to 0 at point B on the beam up here. So the left hand side will become 0 because the y value is 0, so we're multiplying by 0. But on the right hand side of the equation, we now place 6 wherever we have an x value. So x is 6, so 6 in the first term. X is 6, so 6 into the second term. And x is 6, so 6 into the third term. The C2 term we know has disappeared, but the C1 term is still in the equation. So C1x becomes C1 times 6. We're going to consider all the terms on the right-hand side here because both brackets have positive values inside of them. So evaluating the equation, on the left-hand side we have 0. On the right-hand side of the equation we have 1,040,000 plus 6 multiplied by C1. Rearranging for C1, C1 is negative 173.3 times 10 to the 3 Newton meters squared. So now we've calculated constant C1, which we can add back into equations 2 and 3. Exercise 2m continued, just repeated equation 3 for convenience. So now we're going to calculate the midspan deflection when x is equal to 3 meters. All that means we put the value of 3 wherever we see an x in our equation, and that will allow us to calculate the value of y. So we have an x here, so we'll put the value of 3 here, an x here, value of 3 here, an x here, value of 3 here, and the x in C1, so the value of 3 here. What we notice though, inside the square bracket, the numerical value is negative, so we always ignore negative brackets in our step functions. So evaluating the right hand side above, we get negative 344,810. That's still equal to the negative 8 times 10 to the 6 multiplied by y. We just now simply divide both sides by the negative 8 times 10 to the 6. And that evaluates to 0.043 meters or 43 millimeters. So that's our central deflection here for the beam configuration shown. Next we're asked to find the slope or the gradient at A. That's when x is equal to 0 at this position here. So we're going to put the value of x equals 0 into equation 2, shown above here for convenience. So we have an x, we will put the value of 0, so 0 in here, that means the first term disappears, 0 in here, that's a negative in the brackets, so the second term disappears, and the 0 in here, that bracket becomes negative, we ignore that term. And then rearranging to find y dash, which of course is the slope, dy by dx, we find that becomes 0.0217 radians. Don't forget the angles we calculate from our equation will be in radians because the initial derivation for the engineer's bending theory used radians, and converting that to degrees is about 1.24 degrees. We've also got to determine the slope at B, which is where x is equal to 6, the right hand end of the beam. This time we put the value of 6 for x into each of the expressions. So here's my value of 6 into the expressions. Both square brackets have positive values inside them this time, so all the terms are valid. And again, we've got our constant C1 term there. Evaluating the right hand side of the equation, 186,700, and then dividing throughout by the negative 8 times 10 to the 6, we get a y dash value of negative 1.3 degrees. So we've used Macaulay's method there to find the central deflection of the beam shown here and to find the gradient at the ends of the beam. Exercise 4m. A 5 meter long simply supported beam is loaded as shown in the sketch. We're asked to evaluate 1. The differential equations. That means evaluating the bending moment equation and then integrating to find the slope and deflection equations. In part 2, we're asked to find deflection at the midspan, at the centre of the beam, in this case when x is equal to 2.5 meters. The self-weight of the beam is deemed negligible, so it can be ignored. The Young's modulus for the material is given as 200 giganewtons per meter squared, and the second moment of area is 83 times 10 to the 6 millimeters to the 4. So be careful in this question. The first thing is that the units are different between the E, the Young's modulus, and the I, the second moment of area. One is in meters and one is in millimeters, so we need to convert into meters, I would suggest. Next, we need to calculate the reaction at the left-hand end because we need that in our bending moment equation. And once we have calculated the reaction, we can then use the second-order differential equation of bending to start our process. We need to generate the bending equation for the beam working from left to right. Notice the x is from left to right here. Once we've formed and simplified the bending equation, we need to then integrate it to find the gradient equation. We need to integrate it to find the deflection equation. We then need to look for boundary conditions on our beam where we know either a deflection or a slope. In this particular beam configuration, we can see that the deflection at the left-hand end, labelled as A here, will be 0, and deflection at the right-hand end, actually labelled as B here, will be 0. So those will be our two boundary conditions that we can then use to solve for the constant of integration. Once we've found the constant of integration, we will then have our equations for slope and for deflection. And we can then use the deflection equation to answer part 2 of the question to find the deflection at the midspan when the x value is going to be 2.5 in this case, because the length of the beam is 5 meters, so the midspan is 2.5 meters. If you now think you can attempt the question without further assistance, I'd encourage you to stop the presentation and do so, but I will work through the full solution on the following slides. So exercise 4M. Here's the commencement of the solution. The first thing we need to do is to ensure we use consistent units. So from the question, it clearly states that the Young's modulus, that's the E value, is 200 giganewtons per meter squared. So from the question, E is equal to 200 times 10 to the 9 newtons per meter squared. In this particular instance, I'm going to work the value through in kilonewtons per meter squared, because all my loads are stated in kilonewtons here. So actually I will write the 200 times 10 to the 9 newtons per meter squared as 200 times 10 to the 6 kilonewtons per meter squared, because of course the kilo prefix is 10 to the 3, so I've still got 10 to the 9, but as I said, I'm writing it in terms of kilonewton per meter squared here. We also need to be careful with the second moment of area, the I value given. It's 83 times 10 to the 6 millimeters to the 4. I'm going to convert that from millimeters to the 4 into meters to the 4, and I'm using a unity bracket here, a technique we considered in a previous presentation. So the second moment of area in this particular calculation, I will be 83 times 10 to the 6 millimeters to the 4, and using my unity bracket, 1 meter is equivalent to 1,000 millimeters. I'm raising that to the power of 4 here, of course, so that becomes 83 times 10 to the 6 divided by 1,000 to the power of 4, and that evaluates to 83 times 10 to the negative 6 meters to the 4. So now I've got my elastic modulus in terms of meters, it's actually kilonewtons per meter squared here, and my I value in terms of meters as well, meters to the 4. I am going to evaluate my flexural stiffness, the EI term, because I'll need that in our equations. So for convenience here, that's 200 times 10 to the 6 kilonewtons per meter squared multiplied by 83 times 10 to the negative 6 meters to the 4. Obviously the 10 to the positive 6 cancels with the 10 to the negative 6. And evaluating that becomes 16.6 times 10 to the 3 kilonewton meters squared. That's a unit of EI. Exercise 4, solution continued. I'm now going to calculate the beam reactions. I actually only need RA, but I'm going to calculate both beam reactions for completeness. So our usual approach is to take moments about the left-hand reaction. So we're going to take moments about RA in this case. We know for equilibrium, summation of all the moments must equal to 0. And I'm going to state that clockwise moments are positive. So we're going to take moments about point A, RA, here on our beam left-hand end. So I will have 20 kilonewtons multiplied by 1 meter, that's clockwise, that's positive. I will have 50 kilonewtons multiplied by 3 meters, positive, again clockwise. And I will have 60 kilonewtons per meter multiplied by 2 meters, that's the total force here. And the distance we are away will be the 3 meters here plus 2 meters divided by 2. In other words, a half of the 2 here, so that's 1 meter. Remember, when we have a UDL, we work out the total force from the UDL, which is the 60 times 2 meters, and we assume that to act halfway along that UDL span. So that's 1 meter, that's the 1 meter here. Again, that's going in a clockwise direction about RA, so that's positive. What's going in an anti-clockwise direction? Well, that will be the reaction RB multiplied by 5 meters. So that's why it's negative 5 RB in my equation. What I do now is evaluate for RB, so rearranging the equation and solving for RB. RB evaluates to 130 kilonewtons. I'll let you check that for yourself. To find the reaction RA, we're going to summate vertical forces as part of our process. and we know summation of all the vertical forces equal to 0 for equilibrium. So upward forces, we have RA is upwards. Downward forces, we have 20, so it's negative 20. We have 50 down, so negative 50. And of course, UDL, 60 kilonewtons per meter multiplied by 2 meters, that would be negative 60 times 2. And going upwards, we have RB, so positive RB. But of course, we know from above RB is 130. So rearranging to find reaction RA, that becomes 60 kilonewtons. If you wanted to, there you could just take moments about RB and find RA directly. It's only RA we'll be considering when we generate our differential equations. Exercise 4 continued. So part 1 required us to calculate the differential equations for the moment, the slope and the deflection of the beam given. Notice the work we're going to consider, x will run from left to right here. So x equals 0 is at A, and it runs from there across the 5 meter beam. So let's consider the moment equation. And again, as in the previous presentation, I'm using shorthand notation here. When you see y double dash in my equation, that actually means d2y by dx squared. So starting with negative EI y double dash, and notice from this first slide that the positive bending notation is when the beam is in a sagging shape, moving from left to right. So we're going to generate our bending moment equation as x moves from left to right along the beam. So moving from the left hand end, when x is equal to 0 here, if I move away from that and I look to the left of my particular point on the beam, I will see 60 kilonewtons, that's the reaction at the end, multiplied by x. And that's a positive value here because RA times x is trying to sag the beam. If I now consider the x location to be here on the beam and I look to the left, I still see the RA times x, but now I will see the 20 multiplied by x minus 1, and that's tending to hog the beam, so that's a negative bending moment. So my negative bending moment is 20 kilonewtons, negative 20 here, multiplied by x minus 1. So 20 multiplied by the x minus 1 shown here. If I now consider myself at this position here on the beam, and I look to the left of this point, my bending moments would be, again, the 60 multiplied by x minus 20 multiplied by x minus 1. But now I'd also see 50 kilonewtons multiplied by x minus 3. And again, this is a negative bending moment trying to hog the beam. So negative 50 multiplied by x minus 3. So my x dimension runs from left-hand end all the way along to here. So the bending moment generated by the 50 kilonewton load is 50 times x minus 3 at this particular point here. But also now I have a bending moment generated by the UDL. So I have 60 kilonewtons per meter. Again, it's a negative bending moment, negative 60. That's multiplied by the x minus 3 at this particular position here. X minus 3 would be the distance of the UDL. And don't forget the total load of that piece of UDL here will act halfway along the x minus 3. This distance here is the x minus 3 divided by 2. All that's happened on the next line, I've just simplified this last term. So negative 60 divided by 2 is a negative 30, and x minus 3 multiplied by x minus 3, that's x minus 3 all squared. And I've called that equation 1. As mentioned in the previous presentation on Macaulay's method, we must use the square brackets when generating equations because we're using step functions here, and the square brackets mean that they must be ignored from calculations where the value inside the bracket becomes negative. Next, I simply integrate to find the slope equation. And again, from the previous presentation, very standard integration, we're using the standard form of ax to the n from our previous work. So there's our standard form just for reference. Integrating ax to the n with respect to x becomes ax to the n plus 1 over n plus 1, and we will add our constant of integration appropriately. So, on the left-hand side, integrating the negative EI y double dash, or negative EI d2y by dx squared, that becomes negative EI y dash, or negative EI dy by dx. And then integrating the 60x, that becomes 60x squared upon 2. Integrating the 20x minus 1, that becomes 20 multiplied by x minus 1 squared upon 2. Don't forget we're integrating the step functions here, so the step function itself, the square bracket, is considered to be the x term in our integration process. Integrating the third term, that becomes negative 50x minus 3 squared divided by 2. And integrating the fourth term associated with the UDL, that now becomes negative 30x minus 3 all cubed divided by 3. And here's my constant integration I'm adding at the end. And on the next line, I've just simplified my term. So 60 divided by 2 is 30, so 30x squared. 20 divided by 2 is 10, so that becomes minus 10, x minus 1 all squared. 50 divided by 2 is 25, so that's minus 25, x minus 3 all squared. Finally, the last term, 30 divided by 3 is 10, so that's minus 10, x minus 3 all cubed with my plus c1. I've called that equation 2. And to find my deflection equation, I'll integrate one more time. So for the deflection equation, integrating the left-hand side, the negative eiy dash becomes negative eiy. Integrating 30x squared, standard form, that becomes 30x to 3 upon 3. Integrating the second term, that becomes negative 10x minus 1 to the 3 upon 3. Integrating the third term, that becomes negative 25x minus 3 to the 3 upon 3. And integrating the fourth term here, that becomes negative 10 multiplied by the x minus 3 all raised to the power of 4 upon 4. I have to integrate the constant c1, so that becomes plus c1x, and I add my second constant of integration because I've integrated for the second time. Tidying up, again, 30 divided by 3 is 10, so I have 10x cubed for my first term. I'm going to leave the second term because 10 divided by 3 becomes an irrational number, so I'm going to leave that as negative 10x minus 1 all cubed upon 3. For the fourth term, I can divide 10 by 4 to get 2.5, so minus 2.5x minus 3 to the power of 4, plus my c1x, plus my c2. And that's equation 3. So now I've generated my differential equations. These are termed general solutions because I have the constant of integration within them. So what I need to do now is find my boundary conditions, apply my boundary conditions and solve for the constants, and that will produce my particular equations that I can then use to solve for slopes or deflections anywhere I like along the beam. Exercise 4, solution continued here. Just repeated equation 3 from the previous slide for convenience. I'm going to refer to that in a moment. So let's consider the boundary conditions for this particular beam. Well, we know when x is equal to 0, the left-hand end, then the deflection at that point will assume to be 0. So I've labelled that boundary condition as item 4 here. And we also know when x is equal to 5, that's at the right-hand end of the beam where we have another reaction, we will have again a 0 deflection. I've labelled that boundary condition as item 5 here. Now we need to impose the boundary conditions into the respective equations. So first of all, I'm going to substitute what I've termed as equation 4, but it's really the boundary condition shown above, into equation 3 here. And what you'll find is that the constant of integration c2 is equal to 0. Let's just check that for ourselves. This term will disappear because we're multiplying by a y of 0. If I put the value of x equals to 0, then this term will disappear because it's being multiplied by 0. The second term will disappear because if I put 0 in for the x, then the value of the square bracket becomes negative 1, and we always ignore negative brackets, so the second term on the right hand side will disappear, and the same applies for the third term and the fourth term because the values in the brackets become negative. If I multiply constant c1 by 0, the x value is 0, then that will be 0, and so that leaves me with constant c2, but constant c2 is equal to 0. So that's how we end up with c2 being 0. Exercise 4 continued. Just repeated item 5 from the previous slide. That's the boundary condition when x is equal to 5, the y is equal to 0. That's at this point here. I've also repeated equation 3 again for convenience. Notice I've ignored the c2 constant because we know that's 0 now. So substituting equation 5, or the boundary condition labelled 5, into equation 3 above, On the left-hand side, we will have 0 because, of course, the y is 0, so multiplying the EI by 0 will be 0, so left-hand side is 0. But now, wherever I see an x, I'm now going to put the value of 5. So I have an x here, so that will become 5. I have an x here, so that becomes 5 there. X here, 5, x, 5, and then x against the C1 becomes 5. All the square brackets, of course, now have positive values in them, so all the square brackets have to be considered this time. I'll let you undertake the basic arithmetic and the rearranging required here. What you should find is that constant C1 evaluates to negative 186 kilonewton meters squared. I'd encourage you to check that value before moving on. Exercise 4 continued. Just repeated equation 3 from the previous slide, adding in constant C1 that we've calculated now. So part 2 of our question, we can now find a deflection at the midspan, and that's when x is equal to 2.5 meters, in other words half of the 5 meters here. All we do now is put the value of 2.5 into equation 3 wherever we see an x, and then calculate the value of y. So put the value of x into the first term on the right hand side, 2.5 here, x here, second term 2.5, x in the third term 2.5, x in the fourth term 2.5, and x in the fifth term on the right hand side 2.5. We can now see with the third term here that the value in the bracket is negative. 2.5 minus 3 is a negative value, so we ignore negative brackets in Macaulay's method, and the same with the fourth term here. Again, the value inside the bracket is negative. I can now solve the equation for the value of y, noting that the value of EI we calculated previously, the negative 16.6 times 10 to the 3. So evaluating for y, the deflection at the midspan is 0.0192 meters or 19.2 millimeters. Now for reference, often the allowable deflection stated in codes of practice for beams, in the structural industry particularly, is the span divided by 200. So the maximum deflection often allowed is span length, in this case it would be 5 meters, divided by 200. Just working in millimeters here, that would be 5,000 millimeters divided by 200. So the maximum deflection we allowed is 25 millimeters. From our calculation using Macaulay's method, we estimate the centre of deflection to be 19.2 millimeters. Exercise 4 continued. I put a part 3 to the question. This is additional to what we originally given, and it's beyond the scope of what we need for the work we're considering in the lecture series. But I've just shown you here how you would consider calculating the maximum deflection. So for reference, to determine the location of the maximum deflection of a beam, equation 2 must be equated to 0. Don't forget, equation 2 relates to the slope. So when the slope, the dy by dx, is equal to 0, we will actually have a maximum deflection. However, it is not sufficient merely to equate dy by dx equals to 0, since bracketed terms would then be included, which may not be appropriate, depending on where y max occur. Where does the maximum deflection occur? We know with these step functions, if the numerical value inside the bracket becomes negative, we ignore them. So we need to be careful which brackets we include in our calculations. So it's necessary to make an estimate as to in which section the maximum deflection of the beam may occur, and then determine the slope at each end of this section. If a sign change is found over the section, then a maximum deflection has occurred within that section of the beam. So for example, if we assume that the maximum deflection occurs between, say, x is equal to 1 meters and x is equal to 3 meters of our beam, we could then use the equation 2, the slope equation, put the value of x equals to 1 into the equation. So this is equation 2 from our previous slide, putting the values of 1 into the equation for x. So ignoring all square brackets where the value inside is either 0 or negative, we can evaluate the slope equation. So the value calculated here is negative 156. If we divide that by the flexural stiffness EI, we'll actually get the slope there. But we're not interested in the slope. We're only looking for a change in slope. So I'm just going to leave it as a negative 156. If I now put the value of x equal to 3, which we estimated from above, into the equation, so 3, wherever I see an x, I now put the 3 into the equation. And again, ignoring square brackets, where the value inside is 0, I can evaluate that slope equation. And that becomes to positive 44. So as we have a change in sign of the values from the slope equation, then we must have a 0 slope within that section. So therefore, we must have a maximum deflection. So the sign change occurs, thus the maximum deflection occurs between x equal to 1 meter and x equal to 3 meters. So exercise 4 continued, trying to calculate the maximum deflection here. So using equation 2 for when x is equal to 3, equating it to 0 for the maximum deflection location, we can actually generate a quadratic equation. So from equation 2, our slope equation, we will have 0 on the left-hand side because we're calculating for 0 slope. And on the right-hand side, we'll have 30x squared minus 10 multiplied by x minus 1 squared in the bracket minus 186, the constant C1. That's just basically these terms here written together. What I'm going to do now is expand the bracket. The x minus 1 squared becomes x minus 1 multiplied by x minus 1. Multiply out my bracket in the conventional way we have in previous work. And then collate my like terms together. What I find is I end up with an equation 0 is equal to x squared plus x minus 9.8. And that's actually a quadratic. That's of the form ax squared plus bx plus c, where my a in this case is 1, my b in this case is 1, and my c is negative 9.8. Don't forget we have 1s here. We don't write the 1s, but they're there. Exercise 4 continued. I'm now going to solve this quadratic using the quadratic formula. So just plug in my values into the equation. Quadratic formula is x is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. And I have my a, my b, and my c from the previous slide. Putting the numbers in, evaluating, always two answers to the quadratic. One is 2.67 meters and one is negative. The negative doesn't make any sense in this particular context. It's off my beam. It's a valid answer mathematically, but it's not relevant in the context of the question. So the maximum deflection will occur when x is equal to 2.67 meters from the left-hand end of the beam. All I do now is put the value of x equals 2.67 into my equation 3 that I calculated on the previous slide for the deflection equation. So here, 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 and here. But we can clearly see that this bracket will disappear, the same with this bracket, so they're ignored from our calculations because the value inside the bracket is negative. All we do now is rearrange and evaluate the equation and find that the maximum deflection y is 0.0194 meters or 19.4 millimeters. If you compare that to the midspan deflection we calculated to be 19.2 millimeters, it's seen that the midspan deflection is a very good estimate of the maximum deflection in this particular beam case. But that calculation was shown for reference.